So could you please tell us about who you are?
Sure. My name is Brent Barbee. I'm an aerospace engineer at the NASA Goddard Space Flight Center. Uh, I also am adjunct faculty at the University of Maryland, College Park, and uh, largely involves researching and designing various kinds of missions to the asteroids of our solar system, especially planetary defense missions that we would use to help defend ourselves against an asteroid or comet. I teach courses about that at the University of Maryland, graduate courses, and I also teach about interplanetary navigation and guidance at University of Maryland.
Right. So why do you want to become an aerospace engineer?
Well, when I was a pretty little kid, I had the idea that I wanted to do aerospace engineering. So from the time that I was really young, it was just something that I knew I wanted to do, even though, of course, when I was really young, I didn't know exactly what it entailed. But my grandfather was a fighter pilot in World War II, and he continued to fly after the war. He taught my father how to fly, and they taught me how to fly as well. So I grew up as a pilot, and so I was always interested in flight. But I was also really interested in science fiction, which got me interested in space flight. So it was just, it was kind of a natural thing for me to go into.
What is combinatorial optimization and how can it be used in spacecraft?
So combinatorial optimization involves finding optimal combinations or permutations of things. So an example of that is the so-called traveling salesman problem, where you have a map with a bunch of cities on it or a bunch of locations on the map, and you want to find a route for a so-called traveling salesman to take to visit various, some set of the places on the map in some kind of an optimal way. Maybe on the map, it's find the path that takes the least time or the shortest path distance or something like that. Well, for spacecraft missions that involve multiple destinations, we're presented with the same kind of problem. So, for instance, suppose we were going to send a spacecraft to multiple asteroids. Let's say we wanted to choose a set of 10 out of the many thousands, tens of thousands of near-Earth asteroids that we know of, and we want to choose 10 and also choose the optimal order and minimize the propellant used by the spacecraft. That's one example. We also have that same class of problem when we're, let's say we're trying to send a mission to the outer planets in the solar system, like Jupiter, Saturn, Uranus, Neptune. Well, we'd probably like for the spacecraft to do some close flybys of the inner planets, like Earth and maybe Mars, something like this. And so you're going to have this optimal sequence of flybys for the spacecraft to get a gravity assist from each planet. And so it's the same class of problem. You want to figure out which planets you want to do a flyby of and in what order to do the flybys.
And what is parallel processing?
Parallel processing is the idea that you can take a computational problem. So suppose you've written a computer algorithm that solves a particular problem. But suppose that it's a big problem. And so what you'd like to do is you'd like to adjust the code so that the code will distribute the computational work required to solve the problem across many different cores in the CPU, in the central processing unit, or multiple different CPUs, each of which might also have multiple cores. So it's a way of spreading the workload over essentially multiple processing units in a computer. And so, the time it takes to complete the total problem or to solve the whole problem is reduced because now you're solving parts of it simultaneously or in parallel on multiple different processors. And so you can cut down the computational time significantly.
You also do work on simulation and modeling. What are some of the challenges associated with creating a fully accurate simulation?
Well, one of the, I guess there's two main challenges. One is having a complete and correct description of the physics and the dynamics. So the model is only going to be as good as what you know that you need to model, right? So if you are unaware of some part of the physics that's actually going on and you don't include it in your model, then it can be very frustrating to figure out why the model isn't producing results that match what you would observe for that kind of a system in nature, for instance. And then another challenge for producing accurate models is figuring out a good way to validate the model, right? So if there's a particular example of the type of system that you're attempting to model, and it's something that occurs in nature, so you can, and it's accessible to you, you can observe it, well, then it's, you can collect those observations, and then you can compare to those observations. Once you believe you've provided inputs to your model that should match the inputs going into the natural system. And so that's a way that we can, verify our models. And sometimes if somebody else has already done that work, then you can compare your model to the results they publish for their model, that your model is accurate. One of the challenges comes when you're developing a new kind of model, and it's modeling something that isn't easy to observe. So, for instance, on the DART mission, which NASA's launching in November 4th, East Coast time. So that mission is going to a binary asteroid named Didymos, and we've observed Didymos with telescopes and radar from far away. The asteroid is far away from Earth, but we've observed it with telescopes and radar on Earth. So we know some things about how two bodies in that binary asteroid system move relative to each other, but we can't see it up close and personal. So we don't have all the details of how it's moving. But nevertheless, we're still endeavoring to create computer simulations of how we think it's moving, based on the best available information and knowledge about other binary asteroids that we've collected some observations from. We're kind of piecing that together to make our best educated guess at what the binary asteroid system is doing before the spacecraft gets there. And then, after the spacecraft has encountered the system, then we'll have more information and we can update our models.
Since you also work in creating interplanetary trajectory mission design, can you explain the process of creating a proper trajectory for a spacecraft to follow?
Sure. So for interplanetary missions, the mission phase is usually Earth departure, and then a phase where the spacecraft kind of cruises in interplanetary space out there, orbiting the sun, kind of the way that the planets and the asteroids do, and it follows the path around the sun, and then eventually it'll get to the destination. So we have computer algorithms that we've developed over the years that what we do is we take what's called ephemeris data, which tells us where all the planets and the asteroids are that we can track. It's a computer model of where they are and what their velocities are at time through dates in the distant future. So we put those ephemeris data for the planets and the asteroids into the computer, and then we run our computer algorithms to say, all right, so here's a range of dates when we might like to fly this mission. And we run the computer code to analyze, spacecraft departing from Earth on each of those possible dates, and then solving for, using the orbital physics models, what is the path through space under the influence of the sun's gravity and the spacecraft's thruster and other things that will cause the spacecraft to then arrive at the future time. And we can let the amount of flight time vary. We can let the computer code try different flight times within bounds that we set. And it'll solve the orbital physics equations for those sets of constraints, and then say, hey, here's a flight path that is mathematically valid that will get the spacecraft where it wants to go. And this goes back to your question about parallel processing. Oftentimes there's many different possible paths, and we want to find the most efficient paths that maybe use the least amount of spacecraft propellant or something like that. And so what we'll do is we'll use supercomputing clusters, and we'll close out the cluster, and we can, we can get back the answer much more quickly, because we had a lot of CPUs chewing on the problem simultaneously.
Mhm. Why do you think it is important for humans to have accessibility to nearby asteroids?
Well, asteroids are some of the most unique bodies in the solar system. They simultaneously hold the clues to our ancient past and the keys to our prosperous spacefaring future. So the asteroids from the ancient days of the solar system's formation, billions of years ago. And unlike the planets, the asteroids didn't undergo all of the weathering and processing that the planetary material has gone through. So, our planet is tectonically active. We have plate tectonics moving. We have volcanism, volcanoes. We have weather, wind, rain, erosion, oceans. We have all these processes, vegetation and plant growth, and it's changing everything. The chemistry of our planet is evolving, and so a lot of the chemical markers for what were like forming have been covered up or erased. Well, not so in the asteroids. So by visiting the asteroids and collecting samples from them, like NASA's OSIRIS-REx mission to the asteroid Bennu has done, it's bringing the samples back in September of 2023. By studying the chemistry of those samples, we can gain a in the early solar system. It helps us revise and update our models for how the solar system formed and evolved to its present state. It helps us answer questions about, how life began on Earth. Even those things are all connected. So, and then asteroids contain a lot of hydrated minerals, which means you can extract water out of asteroid material, and you can use that. Future astronaut crews could use those resources for drinking water, radiation shielding. Water can be broken down through electrolysis to make oxygen and hydrogen, so produce rocket fuel that could also be used by future astronaut crews. So asteroids provide information that we can't get anywhere else, as well as resources that we could potentially use. We could even process that material to build parts for spacecraft, or even entire rotating space stations out in deep space where people could live and work and have families. So the possibilities for the future are really exciting with asteroids. The other important piece is that they, besides those opportunities, they also send so small asteroids hit our planet all the time, and they burn up high in the upper atmosphere. But back in 2013, we had an asteroid about 20 meters in size come in over Chelyabinsk in Russia and explode over the city. It was a half megaton explosion, and it injured over 1,600 people and caused over $30 million worth of damage. And that was only a 20-meter size asteroid. There are, many millions of those flying around the solar system in near Earth space that we haven't found yet. And there are other larger ones that could cause significantly more damage if they hit us. And we're very motivated to find all the undiscovered near-Earth asteroids that could do us harm, and also be prepared to mount a defense if we ever discover one that's on its way to hit us. So NASA's deploying the INEO surveillance mission, Near Object Surveillance Mission, or NEOSM. It's a infrared space telescope that's going to the Sun-Earth L1 Lagrangian point, where it'll stay there and it'll conduct a survey to find all these undiscovered asteroids much faster than we could do it if we continued to rely on ground-based telescopes. At the same time, at NASA, we're also conducting research, including in partnership with other government agencies, to develop plans and designs and simulations for systems we could use to defend ourselves against an incoming asteroid if we ever had to.
Since you work on how we can deflect hazardous asteroids and comets, let's say in a hypothetical situation where there is a confirmed threat that a large comet or asteroid could impact the Earth. What are some of the ways that we can deflect or even destroy it to prevent its impact?
No, good question. Um, so currently the three most mature concepts for how to do that are the kinetic impactor, a nuclear explosive device, and the so-called gravity tractor. And I'll explain what each of those is. There are some other systems that are starting to be considered as well. One is called ion beam deflection. I'll talk about that a bit too. Um, and there are some other concepts that have been put forward as well that are less technologically ready than the ones that I've listed. So, kinetic impactor is basically a spacecraft that comes in at really high speed and hits the asteroid. You know, two cars colliding, except one of the cars is really, really small compared to the other car. The spacecraft is a lot smaller than the asteroid, but it's moving really fast relative to the asteroid. And if you can pack some mass onto the spacecraft to help it out, the spacecraft can change the asteroid's momentum by just a little bit. And it's enough to nudge the asteroid off course. If you do it far enough in advance of the Earth impact date, it can be enough to cause the asteroid to miss the Earth instead of hit it. And the DART mission I mentioned, which is launching next month in November, is going to be our first test of that system, a kinetic impactor demonstration. So the other technique is a nuclear explosion. So with a nuclear device, and this is a very powerful technique because nuclear systems have the highest energy density of any practical technology known to our science. And the way it works is you take the nuclear device into space, you bring it near the asteroid, rendezvous with the asteroid, so you're kind of flying along with the asteroid around the sun, but it works on a high-speed approach too, like a kinetic impactor would. But what it does is the nuclear device detonates close to the asteroid's surface, and the radiation from the device, from the explosion, irradiates a thin layer of material on the asteroid's surface and kind of quickly superheats it, and it then blows off into the zero pressure vacuum of space, and that imparts kind of a quick impulse to the asteroid, which can be a very powerful impulse depending on what size of a nuclear device you send, and that will also nudge the asteroid off course more forcefully than a kinetic impactor would. The other thing you can do with the nuclear device, because it's so powerful, is you can also put it close enough to the asteroid and choose a big enough device that you can blow the asteroid apart, and we call that a robust technique that we might use if there's not much warning time, because in order for a deflection to be successful, you have to do it far in advance, probably at least 10 years in advance. But with the nuclear device, you can disrupt the asteroid with shorter times, so it has that advantage. And then the gravity tractor is where you take a spacecraft and you bring it close to the asteroid and then have it use its thrusters to just sort of station keep near the asteroid. And you'd like the spacecraft to have a good amount of mass to it. Well, great propulsion system, like it uses ion thrusters so that it can thrust for a very long period of time without requiring too much propellant. And so when the spacecraft does that, the gravity of the spacecraft itself, because remember, all objects with mass have gravity, even if it's really tiny. And so the spacecraft's gravity will gradually pull the asteroid off course, very, very gradually. So again, it's the sort of thing you have to do far in advance in order for it to be effective. And you can make the gravity tractor more effective if you include some sort of a robotic system on it that can actually go down to the surface of the asteroid, collect the asteroid, maybe a boulder or something like a big boulder off the surface of the asteroid, maybe a few tens of metric tons worth of material. And so that way the spacecraft can basically make itself more massive by using the asteroid's own material against the asteroid, if you will. And so that would, that we call that the enhanced gravity tractor concept. And so if that could be made practical, that would be a lot more effective than a gravity tractor that only carries the mass we could send with it from the Earth, which is limited by our rocket performance. The other idea that's started to be studied recently is called ion beam deflection. And so a minute ago, I mentioned the solar ion propulsion system, which uses solar electricity and propellant like xenon gas And what it does is it basically ionizes the gas and then uses electromagnetic fields to propel the charged particles out the nozzle of the thruster. So what you get is a very high exhaust velocity, but a low exhaust mass. And so the high exhaust velocity makes the thruster very efficient. It kind of sips fuel, like a very fuel efficient car. But it also means that because the exhaust is low mass, it accelerates the spacecraft very slowly, as we call it low thrust. But that actually works out pretty well for station being relative to an asteroid. It also works out pretty well if you just take the ion thruster and just point it at the asteroid. And so you're just firing the ions right out the thruster nozzle at the asteroid. And like I said, that ionized exhaust has momentum. And so by conservation of momentum, if you fire all that at the asteroid, it's going to gradually push the asteroid off course, in the same way that the spacecraft's gravity would gradually pull it off course. So that's another way to do it. So those are really the four techniques that are being studied right now. And next to perform our first actual test of one of those techniques, which is the kinetic impactor.
Mhm. So what would you say? Your toughest? I can't speak. What has been your toughest accomplishment so far?
Oh wow. So let's see. Well, so back in around 2010, NASA was starting to study the idea of sending astronauts to go visit asteroids. Considering that. And so at the time, we didn't really have an understanding of what the mission accessibility space looked like for asteroids. And so suddenly we needed to know that. And at the time, if I recall correctly, there were about 7,000 near-Earth asteroids known. And so we had to come up with a way to set all possible trajectory options for that, very large population of objects, and figure out an efficient way to assess those trajectory options and rank them, and sort through that big data set and make it understandable so we could really understand what our options were. And we didn't have a lot of time to do that. So I worked with my colleagues to develop what was named the Near Earth Object Human Spaceflight Accessible Targets Study, or NHATS was the acronym. We pronounce it NATS. And it wound up working really well. At the time, there was skepticism that we would actually be able to perform such large-scale interplanetary trajectory processing for such a large population of potential destinations. But we did it. We got it done. We used parallel processing and combinatorial optimization, the things you asked me about before, and wrote some new code, some new algorithms that made it possible. And then after completing the study, we said, well, we're discovering new asteroids all the time, so we should automate this system so that every time we discover new asteroids, this system will automatically calculate, how accessible they are for missions. And so over the next couple of years after that, I worked on automating the system. And we got that working too, and it's been up and running in an automated way ever since for the past 9 years. And it's still, producing new results every day that are helping to inform what particular asteroids we're interested in pointing our telescopes at to gather more information about those targets because of their potential mission accessibility. So that was a tough project that's it's really paid off very well.
Mhm. And what is a big milestone that you're looking forward to in your research?
Well, the milestone, the nearest term milestone, I would say, is the impact of the DART spacecraft with its target, which is the Didymos Binary Asteroid System, which will take place about a year from now, of next year, 2022. And I'm really excited to see the data that we collect from that mission. It's going to really teach us a lot about not just binary asteroids, but the response of an asteroid to a kinetic impactor spacecraft. And one of the big things that we don't understand fully about kinetic impact is that, beyond just the momentum carried by the spacecraft itself when it hits the asteroid, the energy of the impact is also going to mobilize ejecta out of the little crater that the spacecraft makes on the asteroid's surface. And the physical processes that govern the ejection of that material from the crater, we understand the physics in principle, but we don't have good models for that because we've never had a chance to actually go in space and collect data on that physical process. So, computer models right now generate a lot of different possible results for how much extra momentum we'd get from the material that is ejected off the asteroid. And so that's a mystery right now, and DART's going to provide data to help to gain an understanding of that phenomenon and characterize it. And that's important to understand for future, kinetic impactor missions. So that's an important milestone. And I suppose the next thing after that would be the return of the samples collected from the surface of the asteroid by the OSIRIS-REx spacecraft. So I was fortunate to work on the flight dynamics team for the OSIRIS-REx mission during the design and launch of that mission. And so that was back in 2016. And I'm really looking forward to seeing it complete its mission in 2023.
And to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Well, my first piece of advice is to tell the truth. There's nothing more dangerous than a dishonest engineer. So always tell the truth and always speak forthrightly. It's important. Good communication amongst engineers and scientists is key when you're designing such complicated missions. Involved in making these very complex systems, work correctly, even in the face of large uncertainties, and dealing with lots of contingencies really requires, a lot of dedication and teamwork. So those are focused on. And the main ingredient to make it all come together is good old-fashioned hard work. So, put in the time, especially during your younger years, when you're in high school, when you're first starting college and grad school, those younger years of your life, that's the ideal time to really be investing in, reading and learning how to program, learning how to write, learn how to write really well, learn how to write good presentations, learn how to write good papers, learn how to publish in the scientific literature, and learn how to be part of your engineering and science community. Those are all really important things. And, sometimes it can seem hard at first, but if you invest that effort during those critical years, then, you'll have opportunities to really establish your life. And then you'll get to just enjoy reaping the benefits of that for, the vast majority of your life that still lies in front of you. So do the work, because there's no substitute for hard work, and do it early and often. That's my advice.
All right. Well, thank you for joining me, and thank you for letting me interview you. That was really good.
My pleasure. Best of luck with all your endeavors.
Thank you.